Alright, so today I'm going to be explaining another important paper with the title Random Walk Graph Neural Networks. This NeurIPS paper in 2020 is very important. Graph neural networks have become the de facto tool for performing machine learning tasks on graphs. Most graph neural networks belong to a family of message-passing neural networks. These models employ an iterative neighborhood aggregation scheme to update vertex representations. Then to compute vector representations of graphs, they aggregate representations of the vertices using some permutation invariant function. One would expect the hidden layers of a GNN to be composed of parameters that take the form of graphs. However, this is not the case for message-passing neural network since their update procedure is parameterized by fully connected layers. So we propose a more intuitive and transparent architecture for graph structured data, so-called random walk graph neural network. The first layer of the model consists of a number of trainable hidden graphs which are comparable against the input graphs using a random walk kernel to produce graph representations. These representations are then passed onto a fully connected neural network which produces the output. One of the main challenges when designing neural networks for graph is how to deal with permutation invariance. Any permutation of vertices of graph gives rise to structurally identical graphs. Therefore, the output of a GNN is necessary to be same regardless of the ordering of graph's vertices. A graph is commonly represented by its adjacency matrix and possibly by a matrix that contains the attributes of its vertices. Given the adjacent matrix A of a graph G, the model is necessary to produce the same output for all matrices PAP transpose, where P denotes P in pi denotes the set of all n by n permutation matrices. But most message-passing neural networks achieve that by applying some permutation invariant function to vertex representations such as sum, make, maximum, mean operators, and others. Other GNNs achieve invariance by imposing an ordering on the graph vertices, usually using some heuristic. In this paper, we propose a different approach. We capitalize on well-established concepts from graph kernels, and we employ functions for comparing graphs that are invariant to permutations of their vertices of their inputs. So it compares the input graphs against a number of hidden graphs whose adjacency and attribute matrices are trainable. So the proposed model contains n hidden graphs. The graphs may differ from each other in terms of size. These graphs may be either unlabeled or their vertices may be annotated with continuous multidimensional features. So in contrast to existing approaches, in this paper to map input graphs to vectors, we compare them against the model's n hidden graphs. So performing a random walk on a direct product graph of two graphs G and G prime is equivalent to performing a simultaneous random walk on two graphs G and G prime. As mentioned above, random walk kernels count all pairs of matching walks on G and G prime. If we assume a uniform distribution for the starting and stopping probabilities over the vertices of G and G prime, the number of matching walks can be obtained through the adjacency matrix of the product graph. So the p-step random walk kernel between the two graphs G and G prime can be written like this. And so the proposed random walk neural network model computes a slight variant of the p-step random walk, which calculates the number of common walks. This is the This is how we calculate the number of common walks of length exactly p between two graphs. So this is the overview of the proposed random walk neural network model. So we have, for example, different graphs, G1, G2, G3. These are hidden graphs. And we compare our input to these hidden graphs. Now we can compute the kernel that counts the number of walks, exactly a walk length, exactly p between the two graphs. And this is element-wise product between two matrices. And these are the implementation details that they use: chronicle, product, and vector operators. They are linked by this well-known operator. And so they did some experiment on different data set, like cycle data set, which is completely different from the ladder data set, and star data. Different data set. You can see what happens if we apply this model. And also they did classification accuracy on some graph classification data sets like mutage and DND, NCI1, proteins, enzymes,